Een hele eer voor mij om als voorzitter van de Wetenschappelijke Raad van de Brandweer deze prijs uit te reiken. Dat doen we voor de 5e keer. En het is eigenlijk georganiseerd door het IFV-VVBA, wat Eli al zei. En het is misschien goed om nog even, voordat we echt starten met het programma, nog even de aandacht te vestigen op de Vereniging van Brandveiligheidsadviseurs. Die eigenlijk een selectie heeft gemaakt van de 12 inschrijvingen die er waren. Er waren 12 inzendingen. Die hebben een hele hoop goed werk gedaan om daar 3 uit te selecteren. Dus het is sowieso een eer dat we dadelijk 3 presentaties krijgen van studenten die zeg maar genomineerd zijn voor deze prijs. Nou, de VVBA die organiseert jaarlijks een aantal kennis- en expertdagen. Dat doen we, en dat doen ze in samenwerking met Brandweer Nederland. En dat is denk ik een hele goede zaak waar ik ook in die zin nog even aandacht voor wil vragen. De laatste was eentje over computational fluid dynamics, geloof ik. En daarmee hou je eigenlijk ook een aantal onderwerpen levend en ook onderwerp van discussie. Nou, ik zou jullie willen verwijzen als jullie meer over de VVBA willen weten om naar de site te gaan, www.vvba.nl. Dus schrijf dat vooral eventjes op. Goed, ik begrijp dat we staan een beetje onder spanning. Het programma is iets uitgelopen en we worden natuurlijk allemaal hongerig. Maar we hebben natuurlijk nog eventjes een exquise onderwerp waar ik jullie speciale aandacht voor wil vragen. We hebben 3 presentaties en na de presentaties zal ik bekendmaken wie van de scriptie de prijswinnaar wordt. Dat betekent dat we even een streng programma volgen. Presentaties van 10 minuten. Ik ben streng en rechtvaardig, maar wat tijd betreft meedogenloos. Goed, ik wil als eerste Hilco Hiemstra vragen om zijn presentatie te houden. Hilco, aan jou de vloer.
So, good afternoon. My name is Hilco Hiemstra. I'm from the Netherlands. I did my master at International Master of Fire Safety Engineering, and my thesis, I wrote it at Lund University. There's many research done on fires in residential buildings, and also that it's important that insulation has influence on the fire behavior and also the building content. We already know that, but what I did during my thesis is I compared how we built in the 70s and how we build today, and also for the building content. It's also changed during the last decades, and I make a comparison between these developments and show what the results are. I only have 10 minutes, so I will do it very quickly, and in the end I will give a short conclusion. So at the top I have how the structure changed during the last decades. Let's see, this is the traditional case. Let's say in the 50s. Then we have this, how we build today, and this is a renovated case. In the 50s, before the energy crisis, we didn't have any cavity wall, so it was just a solid brick wall and one lane of glass. Nowadays we have a cavity wall with insulation in it, and the insulation layer is getting thicker and thicker these days. We have a double layer system of glass, and there can be an inlet guard in there to be even better insulated. And we have a renovated case, and in my case, during my thesis, I put the insulation on the inside because we get more information when the insulation is on the inside than on the outside. And we have a secondary glass system. It's just a sort of a double layer glass like this, but then you can make this for a renovated case. Then I have here how the building content changed. In the solid lines, I have the modern furniture, and you can see, I see there is something wrong here. This is traditional. But these solid line is, for example, a sofa, and this is the modern sofa, and this green line here is a traditional sofa. So you can already see there is a lot of difference in these data, and we use nowadays also data from tests of the 70s and 80s. So it's very important to see the difference between these between these items. Let's see. I use this information in a two-zone model. I used B-risk for this research. Why I used B-risk? Now, B-risk is a two-zone model, so it's very easy, and you can compare very quickly different scenarios. B-risk can simulate item-to-item spread ignition. So what I did is I set up a fixed geometry and a fixed place of furniture. So this is my, let's say, my standard input. So what I did, first I start with a fire in a sofa. B-risk can simulate fire spread to, for example, a table or another sofa. So you can generate a more realistic fire curve. Also, B-risk can simulate irradiation for an hot layer. You can imagine if there is a hot layer, you have radiation from the smoke layer that can also ignite items in this room. And you can make a lot of variations, different from fire scenarios. So I think B-risk was for this research a very good program to use. So I have 12 different scenarios. I did 12 different runs to compare. First with traditional. First with traditional furniture, then with modern furniture, and then I did with windows opened and closed to see what is the influence if we close the windows or not. So I made these comparison. And these are the graphs that I have gained. Let's see. So from these graphs we can see, this is the traditional case. There is a dotted line here. This is when the windows are closed. For the traditional case, I only used when the windows are open, because it's not really, you almost get the same results when you get an under-ventilated situation, so the fire goes out very quickly. So from these graphs, you can see that the traditional structure has lower heat release rates and lower temperatures. In the red line, it's the traditional case. This is the structure, and this is a comparison with only for the structure with modern furniture. So the traditional structure has lower heat release rate and also lower. I think the battery is empty now. Lower temperatures in the enclosure. The renovated case is the green line. You can see that's the highest, give the highest peak values. This is because the insulation is placed on the inside, so heat will loss not that quickly, so heat will stay in the room, and that's why the temperatures are higher. Today's structure is in between because the insulation layer is placed on the outside. So there is first a concrete layer, and that's why the heat can the concrete can absorb a little bit of heat, and that's why the temperature is a bit lower than the renovated case. Then the influence of the building content, so the furniture. From here, it's a graph. This is the heat release rate, temperature, and the smoke layer. The solid line is the modern furniture, and you can see that the modern furniture has really an intense fire. It's very short duration, but very high peak values. And the same is also for the temperature. The traditional, you can see that it's a very it's a small fire, but the duration is much longer. Temperature is, it counts also for the temperature. And for the smoke layer, it stays equal because heat can go out steady to the windows. But if you have an intense fire, there's too much mass loss rate that can escape the window. So you get a thicker smoke layer. I did my thesis for life safety to see how it affects the people inside a house. I used the British standards to see when are the critical conditions reached. And from this graph, this is a sort of a summary from all the scenarios. And from here you can see that that the structure doesn't have much influence on life safety engineering, of life safety in the building. The building content is very important for life safety. In all the cases, the modern furniture give very quickly critical conditions. Traditional of the structures become more important when the fire is fairly developed. But in that time, people already are out the building or have to be out of the building. And then also when the windows are closed, so when the fire is under-ventilated, critical conditions is even reached earlier. So smoke cannot go out. So it's you will reach already in 60 seconds critical conditions. And from here you can also see that that not the let's say not the temperature is the main part of this critical condition, but it's a smoke layer that is going down very quickly. So yeah, you have to walk through a toxic gas, and that's dangerous. In conclusion is this, more installations, higher peak values of heat release rate temperatures are reached. Installations matters when it's placed on the inside or on the outside. So in the inside, temperatures will be reached higher than on the outside. When windows are closed, critical conditions are reached earlier, and structure type does not affect the time of critical conditions much, because people are already out of the building. Which influence has the change of building contact on the fire behavior in enclosure? Traditional and modern furniture shows different results. Modern furniture have very intense fires and very short duration. This was my presentation. Thank you.
Goed, Hilco, dankjewel. In verband met de tijd hebben we niet echt veel ruimte voor vragen. Maar ik wil één uitzondering maken. Als er iemand is die de hele week niet slaapt omdat hij die vraag niet heeft kunnen stellen, dan moet hij dat nu even doen. Ik dring niet te lang aan. Maar dat betekent wel, als u vragen heeft in de lunchpauze, probeer dan nog contact te leggen. En dan krijgt u misschien toch nog wel wat meer inzicht in datgene waar u misschien zelf nog mee zit. Hilco, dankjewel. Dan is de volgende Jelmer Feenstra. Graag aan jou de microfoon.
Okay, welcome all. My name is Jelmer Feenstra. I recently graduated from Eindhoven University of Technology as structural engineer, and it's an honor to me that I am allowed to present my thesis project here. I studied the feasibility and effectiveness of two-way coupled fire to thermomechanical analysis. That probably won't say you a lot, but to the right, this picture I show you here of the attacks of the World Trade Center, actually a moment soon after the crash of the second plane. I do not show you this to shock you, but actually this event triggered a renewed interest in structural response to fire. When we look at the typical way we deal with structural fire calculations is by imposing these so-called time temperature curves onto our structure and then analyze its behavior. Now, the main drawback of this is that it can't accurately resemble the randomness associated with fire, and also to a degree not the 3D dependency of the fire on the compartment and the structural system itself. So, in the aftermath of these attacks on the Twin Towers, there was really this request to make use of the more advanced numerical methods we have available nowadays for these types of calculations and analysis. To be more specific, to make use of computational fluid dynamics for our fire simulations, and then combine this with finite element analysis for our heat transfer and structural response analysis. Now, there are various examples to be found in literature in which people combined these systems. Now, what they have in common is, or actually how they work, and they are referred to as coupled CFD-FEM or coupled fire to thermomechanical analysis. And basically what they do is you start with the fire simulation. From there you obtain your thermal data. You then transfer to your next step in your finite element domain, where you analyze how that fire that you simulated influences the temperature of your structural system, here represented by this steel plate. Now, these temperatures will of course induce thermal expansion, so it will displace, some mechanical response will occur, and that you do in the next step, the structural response analysis. Now, you can find various examples from this in literature, but actually what I'm interested in, you can imagine that when it starts blazing the fire and the system starts changing and possibly even fails, that in turn, actually your compartment where you started with changes. And so the structural response could in turn influence your fire. So I'm not only interested in the effect of the fire on my structural response, but also of my structural response back on my fire. So basically, I set out to study this subject, and the first question I asked myself, can we actually do this? Can we combine these systems both ways? And if I then get an idea of this, I want to be able to study how to do this, and how can I do this efficiently without it taking too much time. And in the end, of course, because it's a circular process now instead of a linear process, I would like to comment on its effectiveness. Should we even do these kind of simulations? Now, initially, I came up with this model room to actually limit the various possibilities, which is just a simple office. I assumed an office occupancy class, concrete office with an opening to allow sufficient air, and a thin-walled steel facade as my structural system. Now, for this initial study, I didn't model the structural system as you showed to the right, but actually as just simple steel plates on a frame. Possibly far better to just illustrate a quick simulation of a fire. Here you see an FDS simulation of a room fire. Actually, it's about an hour of simulation, starting from flashover, fully developed, and a decay phase. But my main point here is I want to stress the difference between this one- and two-way coupling. When I do a one-way coupling, I can start with such a fire simulation, just the fire simulation for the fuel duration, and then do the heat transfer analysis and the structural response analysis. But when I want to do it in a two-way coupling, I have to know during my fire simulation if something in that system changed. So I can only do it for a couple of seconds. Ideally, I actually per single calculation step. So I have to do this, as represented by these banner-like arrows, in very small steps. A couple of seconds of fire simulation, heat transfer analysis, structural response, couple the response back, and so on and so forth. Now, when we then redraw my scheme with the pictures I showed you before, here now represented actually the types of analysis with the blue squares, we obtain something like this. And these are actually the various steps I identified as what you have to do to be able to come up with this coupling. So how can we actually do this? Now, you can imagine that when you want to do this one-way coupling, that you can do this by hand. It takes a little time, but it's doable. When you have to do this circle over and over again, actually I should do it in this way, over and over again, it will quickly become a very tedious and time-consuming task. So therefore I learned how to code and wrote a program which could do that and these separate steps for me. And this program I refer to as FDS to Abacus. Sadly, due to time considerations, I can't go into detail on the separate steps, but what you should take from this is that this program, FDS to Abacus, is able to manage both the one- and two-way coupling of such a system, in this case, my system. Now, if we then want to compare these systems, I can then use my program to do various one- and two-way coupled approaches, as shown here. Now, and you can, of course, instantly see that there's a big difference. Now, for the top case, the one-way coupled approach, at the end of the simulation, I found that 7 plates had failed. Where for the two-way coupled approach, only 2. And it was due to failure of plate number 04 that actually failed first, redistributed the fire to a more centralized position. Now, I do want to stress here one important thing, that I don't think this accurately resembles a real-life fire simulation due to a lot of assumptions that had to be made throughout the process. But it does illustrate that taking this effect into account could significantly influence both the fire behavior and the further failure progression of your structural system. So with that, I would like to summarize my presentation, is that I actually set out to couple a fire simulation to a structural response analysis, but also my structural response analysis back to my fire simulation. And by doing this, I found that when we take the one-way coupled approach and a two-way coupled approach, that there is a significant difference in failure of my structural system. Now, when I then go back to this question I asked, should we even do these kinds of simulations, then I sadly have to say it's too early to tell, mainly because most of this research has been based on the computer, so there's no validation whatsoever. That would be one of the next steps. And also, I took a simplified approach to both my structural system and my fire. But still, there are some promising initial results that show that with further development of this tool, I think that it can become a very powerful tool in structural fire analysis and maybe even in fire safety engineering. And with that, I would like to thank you for your attention, and you can find me if you have any questions later on. Thank you.
Jelmer, dankjewel voor je presentatie. Even dezelfde vraag als net. Met name dan voor degene die zegt van ik kan niet wachten. Want ik wil er ook nog even wijzen, daar werd ik net even terecht op gewezen, dat boven hebben jullie allemaal nog een poster staan. Dus dat betekent dat er dadelijk nog tijd en gelegenheid genoeg is om even de zaak af te stemmen. Goed, dan gaan we naar de laatste presentatie. Dankjewel, Jelmer. Dat is Matthias van de Veire. En aan jou ook de microfoon. Succes.
Dankjewel. So good morning, everyone, or good afternoon, rather. My name is Matthias van Veire. I also finished my master's at the International Masters of Fire Safety Engineering. I've done my thesis at the Lund University on the topic of the performance of firefighters' gas cooling. First of all, I would like to mention that this topic wouldn't have been possible without the support of Professor Stefan Svensson, who also is a crew commander at the Swedish Fire Service. And also it wouldn't be possible without financial support of the UL Firefighter Safety Research Institute. So first of all, for all the people who aren't firefighters, let's start with a problem setting. Very often we have to perform interior firefighting. Now, a fire in an enclosure is going to produce smoke, and this smoke is going to build up in a gas layer. This gas layer is hot, it creates a very low visibility, and it also contains unburned flammable gases. Now this means that we constantly have to work in near flashover conditions, which can be a very stressful environment. Now, gas cooling, what is gas cooling exactly? Gas cooling is actually a technique used to reduce those risks posed by the hot gas layer. It is very important to notice that it isn't a technique to handle the fire itself, but it is used to approach the fire safely. Now, how do we do that? That is actually by focusing our attack on the hot gas layer. If we perform this well, then we could theoretically cool the gas layer, we could contract it, and we can maybe inert it. However, if we perform it bad, we can create a lot of excessive steam. Now, what is the reason why I've done this particular topic? Even though this technique is already implemented in several fire stations, that is because there's still limited scientific validation on it. So the technique that is known right now is the pulsing technique. So what were my objectives? Well, first of all, I wanted to experimentally test the different parameters that affect gas cooling. I also tried to isolate the phenomenon gas cooling and look at those different parameters alone. Then secondary, I also looked at the theoretical validation towards the experimental data. And lastly, I also studied the secondary effects, namely the gas layer contraction, but also the buffer time before it reheats again, after we apply the water. Now, in order to achieve those objectives, I built an experimental room. This is based on the ISO 9705 room, which we built in a half scale. We also created a separate room for the fire, so it wouldn't interact with all the measuring apparatus, but also that it would simulate a real fire. We use this technique to advance towards a fire. We used several nozzles to check the different parameters, and we measured temperature, velocities, heat release rate, and the layer height. So you can see there were heat measurements at the front and also at the back of the room. This is, those are some photos of the different setups. Now, the procedure, the aim was to create a gas layer of 160 degrees Celsius. We used a pre-burn of 90 seconds, so we also always had the same temperature, and then we applied the water. The aim was to decrease the gas layer temperature to 100 degrees Celsius. After that, we continued to use a post-burn of 5 seconds to see what happens after we have applied the water. In total, there were 44 tests that were performed. The most important findings were the droplet size versus the reach, short pulses versus long pulses, gas layer contraction, different spray patterns, and the theoretical validity. Since I only have a limited amount of time, I will only discuss the first three. And I will start with the layer height. Why do I start with this? Well, first of all, to show you exactly on a video how the experiments were conducted. But for the layer contraction, we did some theoretical calculations, and we saw that there was only, at these temperatures, there was only a reduction possible of about 10%. So we had a gas layer of 80 centimeters, so that would mean that you could only about change it for 8 centimeters if you have 100% efficiency. So you can see the nozzle here. And as you can see, or might not see, there wasn't a very big difference in the gas layer contraction. Now, more interestingly, there were some very nice remarks on the reach versus the droplet size. Before I explain what I'm trying to say with this, there are two charts here which show the temperature versus time. Both of these charts are tests that were used with the same nozzle. But what is the difference? We used, on both tests, 5 fast shots of 50 milliliters with 2 seconds in between. And this was done to use the same volume and the same flow. Now, the big difference here is the pressure. As you can see, we have a pressure of 3 bar and a pressure of 4 bar. As we know, when the pressure increases, the droplet size will decrease, so the evaporation will be faster. Also, if we increase the pressure, the velocity will increase, so the reach of the stream will increase. So more water will hit the ceiling or the walls, and this can result in a lot of excessive steam. Now, you can clearly see that at 4 bars, so the highest pressure, this first effect, the droplet decrease, outperforms the inverse effect of the increased steam. So there was a way better cooling at 4 bar. Another interesting thing that we saw was that when we compared the different short bursts that are taught to the firefighters right now, we compared that with one long continuous stream. So first one is the same experiment as I showed you earlier. The second one is a continuous stream with the same amount of water, but it only lasted for about 2.5 seconds. Now we can see those temperature measurements were in the front. We can see that actually the 5 short bursts have a slightly better cooling effect. But if we look at the longer bursts, we see that it takes a longer time before it starts reheating again. Also very interesting, it is only slightly less. And then lastly, we see that everything happens in about 1/5 of the time. When we look at the back temperatures, this is where we see the big differences. In the short bursts, they produce a very lower cooling compared to the longer bursts. There's a difference about 20 degrees Celsius. So this is small on the small scale, but if you would enlarge the scale, these differences would be even bigger. So the conclusions. First of all, the decrease in droplet size due to the pressure increase outperformed the adverse effects of the reach increase. The long pulses also proved to be more effective in cooling than the small pulses. This was because less smoke would be re-entering and there would be a better cooling over the whole room. There were no layer height changes seen at these experiments, at these temperatures, but the initial increase recovered very fast, so there were no negative effects seen. We also saw that larger droplets, this wasn't shown here, provided a very good cooling at the back and often showed a bigger buffer time as well. And there was never a complete cooling of below 100 degrees Celsius possible at this setup. So research is never complete. There is still a lot of future work. For example, we want to work with movable nozzles, so more water gets sprayed across the whole room. I think it is also very important, as Ricardo already said, that we should focus us on the inerting of the gas layer. Also, we might be able to focus on larger droplets rather than only on the small droplets. Gas analysis would also be very important at the nozzles level because we want to know if this firefighter is going to be burned by the steam. Full-scale tests. Also, the scaling effects would be very interested to study. And then lastly, we should also use a sootier fuel, so more smoke is going to be produced. I would like to thank you for your attention. You can read the full report on the IMFSC website, and you can always ask me, you can contact me by mail. Thank you.
Oké, Matthias, dankjewel. Ik kijk nog even rond. Prima, dan ik denk dat je dadelijk misschien nog wel bij de poster wat vragen krijgt. Goed, dank jullie wel. Ja, dan is nu het moment daar. Waarin we toe moeten naar het judicium, zal ik maar zeggen. Wij hebben als jury de 3 scripties, de 3 onderzoeksrapporten beoordeeld. Zoals die net zijn gepresenteerd. En ik wil nog even mijn complimenten uitspreken voor de heldere en duidelijke wijze waarin jullie de zaak gepresenteerd hebben. Het zijn toch vaak complexe studies. En ook de complimenten dat jullie echt gehouden hebben aan de tijd. Dat is ook soms een kunst. Goed, ik zal even inzoomen zeg maar, op waar hebben wij nou op gelet. Ik ga niet de criteria noemen van de VVBA, die kun je ongetwijfeld op de website zien. Ik wil nogmaals wel even benadrukken dat we 12 inzendingen hebben en 3 toppers zitten hiervan. Dus daar wil ik op zich al meteen even een applaus voor dat dit echt de 3... Dank jullie wel, de 3 genomineerden zijn op basis van die 12 inzendingen. Hoewel, zeg maar, met de criteria naar VVBA, het lag allemaal erg nauw bij elkaar. Het is allemaal heel hoog niveau. hebben wij als jury zeg maar gelet op, naast die aspecten van de VVBA, gelet op het innovatieve karakter van de scriptie, maar ook de spraakmakendheid en de relevantie van het onderwerp en ook van de resultaten, de wetenschappelijke onderbouwing en de toepasbaarheid voor de brandweer zelf. Nou, het zijn alle drie goede wetenschappelijke onderzoeken, hebben we geconcludeerd. Een mooie ontwikkeling is dat onderzoeken zich eigenlijk steeds meer richting woningbranden, brandontwikkeling en brandbestrijding richten. En dat draagt bij aan die verbinding tussen wetenschap en praktijk, want daar zijn we natuurlijk erg naar op zoek. Alle drie de scripties hebben een interessant onderwerp te pakken. En alle drie de scripties zijn, zoals ik eigenlijk al gezegd heb, van waarde voor ons veld. Goed. Dan moet ik even kijken of ik niet in de war kom, anders dan gaat het niet goed, de beoordeling. Nou, nogmaals, interessante onderzoeken en ik loop ze even langs. Als ik begin met de scriptie van Jelmer Feenstra, dan is de jury van mening dat het een origineel en vernieuwend onderwerp is, waarvoor veel belangstelling bestaat. En er is ook veel behoefte aan beter inzicht in de interactie tussen thermische en mechanische respons, zoals het net gepresenteerd is. Het onderzoek is sterk theoretisch en fundamenteel van aard. En als haalbaarheidsstudie een goede opmaat voor wetenschappelijk vervolgonderzoek. Nou, experimentele validatie, dat zou naar mening van de jury erg bijdragen tot een verdere acceptatie van deze resultaten. Even kijken, ja. Nou, die jury beoordeelt de betekenis van die scriptie voor de brandveiligheid, de actualiteit als diepgang en de sterke punten van die scriptie die er ongetwijfeld in zitten. De jury heeft wel het oordeel dat de directe toepasbaarheid, de layout en de uitdrukkingsvaardigheid en leesbaarheid als wat minder sterke punten naar voren komen. Je moet altijd sterke, maar soms ook minder sterke punten naar voren brengen. Nou, de scriptie van Matthias van de Veire. De jury is van oordeel dat de scriptie een gedegen experimenteel onderzoek is naar de effecten van druppelgrootte op rookgaskoeling. Het is ook een actueel onderwerp, laat dat duidelijk zijn. En de uitkomsten dragen bij aan een verdere wetenschappelijke kennis en verdieping over dat fenomeen. Het onderwerp is experimenteel van aard en door de laboratoriumopstelling nog niet direct toepasbaar. En daar heb je het net zelf ook al over gehad. Ook de opschaling is misschien interessant. Een aanbeveling hoe de rookgaskoeling toegepast zou moeten worden, dat zou de studie nog waardevoller maken. Nou, de jury beoordeelt de betekenis van de scriptie voor de brandveiligheid en de actualiteit als de sterke punten van die scriptie. En de jury beoordeelt de directe mate van toepasbaarheid en de mate van innovatie als minder sterke punten van die scriptie. Even kijken, want wat ik net al zei, ik mis er nog eentje. Hilco Hiemstra. Hilco, de jury is van mening dat het een interessant onderzoek is naar de effecten van gebouweninventaris op brandontwikkeling. Het onderwerp is op zich niet nieuw. De conclusies zijn in die zin ook niet verrassend, maar wel relevant en bevestigend ten opzichte van andere onderzoeken die op dit moment lopen. Bijvoorbeeld ook de onderzoeken in Zutphen. Een aantal keuzes en aannames in het onderzoek zijn wat minder goed onderbouwd. Nou, de jury beoordeelt ook hier de relevantie, de layout, de uitdrukkingsvaardigheid en de leesbaarheid van de scriptie als de meest positieve punten. Daarentegen beoordeelt de jury de diepgang en de mate van innovatie als wat minder sterk van deze scriptie, wat minder scherpe eigenschappen. Goed, als we dat zo gehoord hebben, dan wat ik al zei, het was moeilijk, maar we hebben toch een keuze moeten maken. En laat ik dat ook maar meteen onthullen. Dat de jury heeft de scriptie van Jelmer Feenstra van de Technische Universiteit Eindhoven uitgeroepen tot de winnaar van het IFV, de 5e IFV-VWBA scriptie van 2016. Nou, Jelmer, dan wil ik je graag even naar voren roepen, want dan zal ik je ook de prijs uitreiken. €1200, zoals je weet, te besteden aan eigen inzicht. Dus dat is een heel mooi resultaat. En ik wil je ook nog hierbij. Nogmaals, dankjewel.
Ja.